In part 1 of this set of MathsCasts, we proved the limit shown here, that sin x over x tends to 1 as x approaches 0. That was relying on x being measured in radians. We'll discuss what happens if x is measured in degrees a little bit later on. In this part 2, I'm going to look at another important limit that we'll need for first principles differentiation. It's the following limit. The limit as x tends to 0 of 1 minus cos x divided by x. The answer is going to be 0, but I'll show you how to prove that. Now we've got the first limit result for sin x over x, the second one is a lot easier to prove because we can make use of the first one. I'm going to examine that function, 1 minus cos x over x. I'm going to multiply it in the numerator and the denominator by the same quantity. In fact, by the quantity 1 plus cos x. That hasn't made any difference to the value of the function. Of course, I should not do this and it would not be valid if 1 plus cos x happened to be 0. But that only happens when cos x is negative 1. That is possible. It happens when x is pi, or odd multiples of pi. However, we're not interested in values of x near to pi, or any odd multiple. In this limit we're interested in values of x close to 0. When x is 0, 1 plus cos x is equal to 2, and that is certainly not 0. So we are allowed to do this. But now writing this function in this way means that we can expand the brackets on top and get 1 minus cos squared x. Furthermore, 1 minus cos squared of anything is equal to sine squared of that quantity. So it's in this form that I'm going to try and take the limit as x tends to 0. Look at the quantity in the right-hand limit. There's a sin x over x there, isn't there? The trouble is it's not just sin x, it's actually sine squared on top. Let's separate it out so that we can see the sin x over x explicitly. Once we've written it that way, we actually can identify the correct limits for all the individual components. As x gets small and tends to 0, sin x over x becomes 1. 1 plus cos x becomes 1 plus 1 is 2, and sine on the top, the remaining sine, tends to 0. So this limit is equal to 1 times 0 over 2. But that's just 0, and so that's the value of the limit. We've got the result we wanted. This limit, along with the one that's got sin x over x in, are the two limits we will need for differentiation from first principles of sine and cos. However, since this MathsCast is now really very short, only just over 3 minutes, I thought I might just show you another interesting limit. This time I want to look at limit as x tends to 0 of 1 minus cos x over x squared instead. We won't need this one in the differentiation, so I'm just doing it for fun really. But it does demonstrate the kind of thing that we do when we're trying to work out limits. The only difference of this from the limit we've just looked at is that extra power of x underneath. Let's collect that with the spare sin x. So there's the first sin x over x that we already had. And remember then there was a spare sin x, but now we've got a new x to go with it. And what's left, let's just look back a moment, it was that 1 plus cos x underneath, wasn't it? Okay, so we can write a 1 over 1 plus cos x. And now we can take the limit again, because sin x over x becomes 1. So that is 1 times 1 times 1 over 1 plus 1, because cos of 0 is 1. That all simplifies to a half. So we can now say with authority that limit as x goes to 0, 1 minus cos x over x squared is equal to a half. All these limits will become a lot clearer once we have an understanding of Taylor series, but that's another story. I'm going to finish there.